Shall we? Now I want to generalize this. I can either give you the foothold of the Armour theorem, or maybe, but I think we will amuse ourselves by proving just a bit more with this elementary method. So for example, take G to be SSAR now. Actually, I should call it S. Never mind. It will appear as S in future discussions. U.
And that's G.
Sorry?
And that's G.
And as G, yes. Okay. Let's be this guy. So claim no invariant matrix on G on D. How do you go and prove that?
Star is about all the upper parts? Just
No, only here.
Okay.
This U one-dimensional group.
Extra zero. Extra zero.
Sorry, this is not the answer. So here is something that if we do have a metric on G mod U, you have this H inside G. Maybe this is H, right? This is a copy of S there, which sits inside, and the metric restricted to that one should be trivial. Right? Maybe I postpone this. I'll prove this as part of the of a more general setting up. I want to prove this. I want to prove about SO2 still. Plane. No G-invariant matrix on G mod A. Now G is SO2. A is lambda lambda A. So this is a general phenomena. So in fact, every A fixed point is P fixed, or is U fixed as well. So you've just seen that, right? I do it in any case. So assume. So this is a general fact about metric spaces. Assume G act on X. Actually, maybe. No. So I want to remember this. P now is this group, upper triangular, 2 by 2 matrices, and this is the same as AU. P isometrically on a metric space. XT. Then, if we have an A fixed point, is already P fixed points. Dilemma. So, obviously, every P fixed point is A fixed point. So I need to show the other equation. So assume you have a point which is A fixed. For U in U, consider dx dqx. To show that x is U fixed, I will show that this is 0. But of course, for A in A, any A in A, this is the same as the metric is invariant. Sorry, here, this is as x is A invariant, this is the same as that. And by invariant of the metric, it is the same as this one. Now, I can choose, I can conjugate U. What is the conjugation of this one by lambda inverse? Stop this. You should know it by heart, I think.
So lambda squared is 1 and 1 lambda squared.
Everyone knows something about root decomposition. Know it, and everyone knows how to multiply matrices should know it as well. And now if you take lambda goes to 1, here, you see that this tends with dx x, which is it. Now this is constant. This is not depends. This depends when A goes to lambda goes to 1. And the lambda goes to 0. So A here depends on lambda. Discussion. But this quantity does not depend on lambda. If it's a constant, then this constant must be 0. X is in XU, and in XA, okay. Now I want to so about this claim. The base point PA and GA is fixed by A ends by T. Okay, now I can argue either using U or using A. Okay. Also wait. By the same argument. assume you do a metric on this, it actually must be the zero metric. Okay. Now I'll what should I do now? Now I want to explain or maybe observe define. I want to define yet another property. In a blank space, X, a generic space. Give it generic space X is metrically ergodic if for every metric space VD from which the G acts isometrically, any G value X with it is essentially constant. Or observation. By taking V to be, I don't know, 0, 1 with a trigger action, metric ergodicity has a ergodicity. So metric ergodicity is a much stronger statement than just ergodicity. I want to discuss this notion. So previously I showed that on some spaces there are no metrics. I want to express this in ergodic theoretical terms. Is this remark clear? If I am metrically ergodic, then every mapping to 0, 1, a mapping to 0, 1 is just a choice of a subset, is essentially constant, means that my subset that I choose is either everything or none. So I want to re-express those claims that I was considering. Let's take it in place. Metrically ergodic. So the proof of this statement is the following. If I have a map S mod U to V, an S equivalent map, the image of U must be well, so just pull back the metric from V to S mod U by this, and get a metric on S mod U. And this metric must be, maybe I guess the statement I made, the way I state the claim was correct, but not in the right generality. What I actually proved is that maybe I should have discussed not metrics, but pseudometrics. A pseudometric is the same as a metric, but then I allow to get the distance between 2 points might be 0, distinct points. Okay, just relax this of metric. And basically I proved that on G mod U, the only pseudometric that I might get is the 0 pseudometric. When I discuss pseudometrics, it's kind of enables me to speak about maps which are not a priori assumed to be injective. Whenever I have a map from S mod U to a metric space V, I can pull back the metric to a pseudometric a priori on S mod U. But this pseudometric on S mod U must be the 0 metric, which means that the distance between every two images here must be 0, so the map is constant. Yes?
Didn't we have the discrete metric also?
Sorry?
Didn't we also have...
So whenever I set a metric on a space, I mean, not discrete, but compatible with the given topology or measurable structure. The discrete metric is indeed an S-invariant metric on the space, but it is S-invariant on the set S mod U for the cost space, but not on the Lebesgue space. It doesn't fit the extra structure behavior. So it's explicitly assuming that things are compatible with my extra structure.
But with the measurable structure, right?
Sorry, so for example, I do have maps from S mod U to V, a priori. I can take, but I don't have measurable maps. So my maps are assumed to be measurable.
So when you when you said no G invariant metric or pseudometric, you meant that the sigma algebra given by the topology given by the metric is the one that's given. This is the compatibility, right? That you want for the metric.
Yes.
So not continuous, you want something weaker.
Okay, so here's an exercise.
Well, in the G space it's the same. Yeah.
No, but yes, homogeneous. Okay, so here's an exercise I want to on G mod H, every measurable G invariant metric on G mod H is continuous. This is general G H. Do you know this fact that every measurable homomorphism between locally general locally LCs, locally compact second count? Do you know this general fact that measurable homomorphism between groups are always continuous? So how do you prove it? What is
Integration, fix one of the variables and do some sort of integration. Phi of x times.
Oh, okay. I guess there is more than one way to express it, but in the heart of it,
So what I mean is that you write down the equation.
the process of integration makes things more regular. Why is it so? So if you dig down deep inside, you see that A of positive measure, so this is the general name. In G implies A inverse contains an identity neighborhood. So basically, if you want to show that a certain metric, whenever I have a metric, I can view just the norm, that is the distance from the identity. If the metric is G invariant on the left, then this contains all the data. So I have some sub-additive or sub-multiplicative norm on G, and I want to show that is continuous. This means that I want to show that every epsilon ball around E contains an open set. So look at the epsilon half ball around E, and use the triangle inequality to show that the and this to show that the epsilon ball contains an open set. Something like that.
So what's the relation of this exercise again?
The relation is that yes, okay. When I discuss ergodicity, first of all, I assume I was proving that on S mod U we don't have continuous metrics or continuous pseudometrics which are not trivial. When I discuss ergodicity, I want to say that there are no measurable maps into spaces. Whenever I have a measurable map, I can pull back the metric, but then I get only a measurable metric a priori. But in fact, it is continuous. So there is no problem. So this is.
Can you define it? The notion of metric and algebraic can be defined as no invariant pseudometrics?
Yes. It's the same. So the metric ergodicity is the same as no invariant constants. So this is, but this is a nice way to view it. For example, so here's another claim. So I'm now playing around this claim just to get a hold on things. Take gamma inside S as a 2R. Oh, let's make it general. Gamma inside S elapse. This means that S mod gamma has a finitely balanced measure. S act on X, metrically ergodic, implies that if you restrict the action to gamma, it is still metrically ergodic. It's the claim. How one goes. Maybe I will prove it to you, but let's see some corollaries. This means we know that S act on S mod U. S is S2. We know that S act on S mod U metrically ergodic by the previous discussion. So it shows that this is metrically ergodic. In particular, here's another non-trivial fact. Gamma act on S mod U ergodic. It's equivalent, for example, to the fact that U act on S mod gamma. Is that clear? Both statements, this is both equivalent. S times gamma, S times U, gamma times U, and from S. So gamma times U act on S, gamma on one side, U on the other. Okay, and I claim this action is ergodic. I know that gamma act on S mod U is ergodic. So what are the This is to say that any gamma invariant function on S mod U is constant. A function on S mod U is a function on S which is invariant for the U action. I can put it back to a function on S. When I map S to S mod U, if I have a function f on S mod U, I go to R or to 0, 1. I can view it as a function on S, which is invariant. And if f was gamma invariant function here, I'll have here a gamma times u invariant function on S. So there are no gamma invariant. To say that gamma act on S mod u ergodic is the same as gamma times u act on S ergodic. And by symmetricity is the same as saying that u act on S mod gamma ergodic. So and this statement has a name. This is called the ergodicity of the whole cyclic flow on S mod gamma. This is the specific case of gamma being S of 2z. I mean, it's a classical fact. But we are about to prove it by proving much more. So we are proving that gamma act on S mod u is metrically ergodic in a minute. And this is a general phenomenon. We prove that whenever a space act on a group act on a space metrically ergodic, also the action of a lattice is metrically ergodic. So let me try to do it. So
So the metric condition also passes after you change the.
this I don't know. I think so. Yes, I think we're by the same. I think writing D here. By the same argument passes. Yes. Thanks for asking this. Okay, so I want to show. Assume you have a gamma input. So I have gamma act here. Actually, I have S act here. But I have gamma inside it. And gamma act here isometrically. So like this. And quantity. And I have some map here. So V is a gamma space on which gamma acts isometrically. X is my is a space which is ME ergodic. This action is ME, but I don't know it a priori for the gamma. So if this would be an S map, an S space, and the map would be S equivariant, it would be constant. Okay, I don't know it now. This is only a gamma space, but now consider the space before considering, I may assume D is bounded by 1. Maybe like replacing it if necessary. Every metric is equivalent to a bounded metric. If gamma acted isometrically on the previous, it still acts isometrically on that one. And if there are no, I will show that there is no gamma invariant map by changing a metric. It doesn't mean anything. And now I want to consider So the thing is that I'm looking at this space, and I can embed X in that space. There is a natural map. From X to L S to B. And this is taking X to, now I need to find a function from S to V. The function that I will find will take S to, well, I can take Sx and fit, right? I do have, this is given. Given two vipers, and X is an S space. Now, observe, I want to observe two things. That this map is indeed gamma equivariant. So the map from given X, I want to say that the map I'm getting here is gamma equivariant. This is clear, right? If I multiply S by small gamma and by gamma invariance of phi, it will go here. And further, it is C is S equivariant. From X to this one. So S act here, and it does act here via the S acts on LSD by its height action on S on the source. Okay, now I want to make yet another observation. I didn't use the fact that gamma is a lattice yet. But now I want to claim that on this space there is a natural metric. On LSV gamma, there is a natural metric. There is an S invariant metric. Let's call it D. So assume you have two guys, alpha and beta. Alpha and beta are, well, there are elements in this guy. There are maps from S to V which are gamma invariant. I can define a distance between those by integration. I would take an L2 distance. So I'm using the L2 distance, and I'm integrating over fundamental domain. For gamma in S. And it doesn't matter which one, by the gamma invariance. So, we constructed this map from S map from X to that space, but this is the metric space. So what do we get?
Big D is 0.
Hmm?
Big D is 0.
Not the big D is 0. It's not that the space is trivial, it's the map is constant. I mean, the assumption that you want to use is that, where is it written? Yeah, the action of S on X is metrically ergodic. My assumption X on X is metrically ergodic. And size constant. This is psi. X goes to little s goes to phi sx. So this map is independent of the coordinate x. So this means that phi is constant to begin with. And this is what I want to show. I want to show that every down map from X to a metric space V is essentially constant. How are we? Time-wise?
31.
Okay, so